Okay, welcome everyone, and welcome online as well. So this is the demo in advance of the discussion paper, which is on at 4 o'clock. We've got an hour to understand more about this subject before we listen to the discussion paper. I think we need to have a fire safety announcement by Judith. Oops. First of all.
Yes.
We just had firemen here actually, but
I know we have. Yes, but it's fine. There's no planned test today. So in the event of an emergency, please evacuate, follow the designated RSS staff fire marshals. I think I'm one of them for Council Chamber, and the nearest fire exit. So we've got one here out the front door where you came in, and there's also one out the back.
Great, okay, thank you. So the full paper is called Parameterizing and Simulating with Causal Models, but the demo is going to focus on Frugal parameterizations. And I think we're kicking off with Robin, and then we're moving on to Dan Manella and Z Lee, who are going to share it between. So we've got an hour, and they've said they're happy to take questions and interruptions.
Yeah, so do just ask questions at any point, and I will try to clarify. Okay, well, thanks very much, Shirley. So yeah, the point of the demo, we sort of thought we'd do it slightly more interactively maybe than usual, and talk a little bit about the software that implements the methods that we will talk about a little bit later on this afternoon. So this is, I will start by presenting some slides, and then she will tell us about the R package that you can use for simulating this method, which is called Causal. And then Dan will take over and talk about the Python package that you can use to simulate from these models. And this is a sort of outline, so I'll give a bit of motivation as to why we care about this particular method of simulation. Then I'll introduce our solution to the problems that I identify. Then she will talk about the Causal package, and then finally Dan will talk about Frugal Copilot, which is the Python implementation of these methods. So why do we care about being able to simulate from models in this way? So I'm just going to give you a little causal example, a story. So the idea here is that we've got a doctor who's got a lot of patients who suffer from type 2 diabetes. And at the first time point here, she can decide to give them either a 0.5 milligram or 1 milligram of semaglutide, which is a drug that's designed to help control your blood sugar. And then 8 weeks later, she's going to measure the blood sugar of these patients. And that's a variable we're going to call Z. And as a result of both the outcome of the first dose that's given and the response that's observed in the blood sugar, she'll then possibly change the dose to either up it to 1 milligram or reduce it to 0.5 milligram or maintain it at the same. And then on the basis of all three of these inputs, these two doses and an intermediate outcome, the final outcome is a cardiovascular outcome called MACE. And that's basically you have a 1 if you suffer from a stroke, have a serious heart attack, or die from some other cardiovascular event, and a 0 otherwise. And this would be obviously a year or two or more later. And then of course our two outcomes, Z, the blood sugar, and Y, the MACE outcome, are all on the same, are both on the same patient. So we're going to assume that they'll be affected by some unobserved confounding, which we're going to represent by this variable U that's a parent of both of those two variables. A very reasonable question to ask might be, what if we didn't dynamically assign B, but what would happen if we just said to everyone, okay, I'm going to give you 0.5 milligram at A and then 1 milligram at B. What is going to happen to the distribution of MACE under that regime, under that implementation? So what we're asking is, what is the density, the distribution of this MACE outcome, given that I fix A to be equal to little a and B to be equal to little b in a causal sense? So the first question is, well, how do we even identify this quantity? So we might think, well, maybe we should just regress Y on the two treatments. But we can see pretty easily that's not going to work, because if we look at the graph, I've just highlighted a path here that will be open if we don't control for the intermediate outcome, the blood sugar. And that's because there's a non-causal path that goes from this second treatment up to blood sugar and then straight down to the outcome. So if I just regress on A and B without attempting to control the blood sugar level, I will get a biased answer. Unfortunately, if I control for the blood sugar, I also get a biased answer, but this time the problem is with A, because if I now control for Z, this causal path that goes through Z to Y is blocked, and therefore I'll be losing some of the causal effect of A on Y when I control for Z. And even worse, actually, when I condition on Z, that opens up this other non-causal path that goes from A to Z, but then back up to U, and then down to Y. And obviously, I don't want to include that in my estimate either. So neither of these two approaches will work. And the problem here is that Z is what's known as a time-varying confounder, and it's affected by previous treatment. So it's affected by A, but it also affects B, and therefore you can't control for it by conditioning on it or not conditioning on it. You have to do something else. Fortunately, this was solved nearly 40 years ago by Jamie Robbins, who showed that what you have to do is use something called the G formula. So here we take the observable distribution, so the 4 variables we can observe, the 2 treatments and the 2 outcomes. We factorize it according to the causal order. And then we can notice that what we really want to happen is for B not to depend on the first treatment and this intermediate outcome. So what we really need to do is get rid of these 2 edges that are going into B. And the way to do that is just to get rid of this factor. So I'm just going to cross it out, and I'll cross out P of A as well. And now what I'll have is a distribution which, excuse me, almost by definition is the joint interventional distribution of Z and Y after I've intervened to fix that big A is equal to little a and big B is equal to little b. And then, of course, what I want is only the distribution over Y. So I just have to integrate that expression over Z, and I get this formula here, which will tell me what the distribution of Y is if I intervene and fix the treatments to some particular values. And this is called a marginal structural model. It's also due to Jamie Robbins. It's structural because it's causal, right? If I change B, it will have an effect on the outcome. And it's marginal because I had to marginalize out Z to get the expression. Okay, and marginal structural models are really very popular in epidemiology because they allow you to control for this time-varying confounding. And I won't go through all these examples, but just to say the first one is essentially the motivating example behind them. So this is what caused Jamie to be interested in developing these models. If you're thinking about something like antiretroviral therapy for HIV, you have as a time-varying confounder the CD4 count. So the CD4 count responds to the level of antiretroviral therapy, but it also will affect whether or not someone should go on to antiretroviral therapy. And therefore, it's very important to be able to analyze that data in a way which removes the effect of the CD4 count from the survival, which is what you're interested in. Okay. So obviously, if you have a model that's useful, it's going to be also going to be useful to be able to simulate from it. For example, to check that the size of a test you have is what it's supposed to be. But all the papers that simulate from them really do it in a very indirect way. So Jessica Young has a couple of papers with Jamie Robbins and Miguel Hernan, both giving different approaches to simulating from survival, time to event marginal structural models, but they have to use special cases of other models that are easier to simulate from, and then compute what the implied parameters are. Vanessa has a paper with a student of hers, Will Havercroft, where they try to simulate from this functional so that it doesn't depend upon A. And they're able to do it, but they have to remove the direct effect of the intermediate outcome on the final outcome in order to get it to work. And it sort of doesn't really generalize to other models in the way we might want it to. And then finally, so Ruth has a paper with Sean Seaman and others where they use additive, fully conditional hazard models and then work out what the implied marginal structural models are. And again, and that's very useful, but it's not so good if you want to simulate from a null hypothesis, because you can't say, I want this parameter to be 0. So lots of very clever people have tried to simulate from these models, but failed. And what that tells us is that simulating from these models is hard. And one of the reasons it's hard is that So as Jamie put it in the 2000 paper, the likelihood for these models is a computational nightmare. So it's very difficult to write down the likelihood for a model like this. And the other reason it's difficult is because the model suffers from something called the G-null paradox. So that was something that was identified by Jamie Robbins and Larry Wasserman in the 1997 paper. So what is the G-null paradox? Well, it basically says that if you take that G formula we saw earlier and just plug in some nice seeming regression models, then you can easily end up with a situation where a null hypothesis you're interested in can't logically hold without imposing a lot of extra restrictions that you don't want to impose. So let's take a simple example. Let's suppose that this intermediate outcome is binary and it's a logistic regression conditional on the first treatment, and there's just a parameter alpha which controls how strong that dependence is. And then y will assume has a linear mean in each of the three other variables separately. So these are nice, simple models. You would think there wouldn't be a problem with this. So we can compute then what the expectation of y is given do A and B. So we just wrap that around here. A and B will just come out. So we have those terms here. And then the expectation of z given do A and B is just the same as the expectation of z given A. So that's just this parameter here, x bit of alpha A. So we end up with this third term, x bit of alpha A times beta z, that comes from the middle term here. And now, under what circumstances would this right-hand side not depend upon capital A? Well, we need two things to happen. So this beta A has to be 0, and either beta Z has to be 0. So that's a very strong assumption because it's saying that Y is jointly independent of A and Z given B. That's this possibility here. Or alpha has to be 0, so that the x bit doesn't depend upon A. And that's imposing that A is marginally independent of Z, as well as that Y is independent of Z, of A given Z and B. So these two possibilities are both much stronger than the model we actually are interested in testing. So it's much more restrictive than the hypothesis we wanted to test. And the lesson here is really just specifying nice models and hoping that when you compute, you'll be able to choose the parameters in order to get a null hypothesis. It doesn't really work that way. Of course, if everything's linear, it's not a problem, right? So if Z had a linear mean in A, so it was just A times alpha instead of x bit of A times alpha, and this can work because now I just need this coefficient to cancel out this coefficient here. So we just need beta A plus alpha times beta Z to be 0. But obviously, that's not going to be possible with most nonlinear models. And what we want to be able to do is to simulate for models which don't impose such a strong restriction on the form of the distribution, right? So we don't want to have a linear mean, for example. Okay, so that brings me to our solution, which is called the Frugal parameterization. So I'm just going to change examples a little bit, and this is a sort of cartoon of the model I was first thinking about when we developed this. So we have some covariates, which are now called Z. So they were called Z in the original model as well. We've got some treatments, which are called X, and we've got outcomes, which are called Y. And the intuition is that we want to be able to simulate from this model here, but such that the causal effect, the marginal causal effect of X on Y has a particular parametric form. So we want a piece of this distribution to be specified over here, but it to be part of a description of the joint distribution on the left. So the things we want to specify are P star of Y given X, so that's after intervention, that's like Py of given do X. And we'd also like to specify, for example, the marginal distribution of the covariates, so just P of Z, and maybe the generalized propensity score, so the distribution of treatment given the covariates. And what we can see here is now we've got two margins of a joint distribution here. So we've got P star of Y given X and P star of Z given X. But we don't have anything that tells us about how Y and Z are related to one another. So we need to add something else into the mix here in order to reconstruct this joint interventional distribution. And the answer as to what it is we need to add is some sort of conditional dependence measure. So really, we sort of borrowed techniques from marginal modeling in order to answer this problem. That's because the causal models that we're interested in are marginal. They're just marginal under an intervention. So what we're going to add in here is some conditional dependence measure for y and z conditional on x. And the main example we deal with is copulas. So a copula is just a bivariate CDF where the margins are uniform 0, 1, continuous uniform 0, 1. You could also use something like a conditional odds ratio if z and y are discrete. And in principle, even if z and y are continuous, you can use a conditional odds ratio, but algorithmically, it's not very pleasant to try and compute things with a continuous odds ratio. Okay, so the Frugal parameterization consists of 3 separate, smooth and regular parameterizations, parametric models for the margin of the past, so that's the covariates and all the treatments. And a piece that parameterizes the distribution of interest, so that's this P star of y given x. And then finally, something which parameterizes this dependence measure. So that could be just the parameters of the copula, it could be the conditional odds ratios or whatever. And what's nice is that if, sorry, this should be a star on this, and it should be a star here. If phi star y z given x is a copula, then we get the following likelihood decomposition for our model. So you just take, this is the copular density here. So we get the margin over the covariates, the propensity score. So this is just P of zx here, these first 2 factors. Then we get the thing that we're interested in. And then finally, we multiply on by the copula. And once you can parameterize the distribution, actually simulation becomes quite straightforward. So in the original approach, we uses rejection sampling. So the idea here is we're going to simulate from P star, and that's just this, but we replace P of x given z by some dummy distribution over x. And because we've got this copula here, the simulation is very easy in the causal model. And then we can take samples, we compute the supremum of the ratio of the target density, which is P, and the density we're actually simulating from. And it doesn't matter whether we have y in here because that part will just cancel out. It's the same in both P and P star. So really just looking at the marginal over x and z. We compute what the maximum is of that, and then we sample uniform 0, 1 variables. And if the uniform 0, 1 variable is less than this expression here, then we keep the sample. If it's greater than it, we throw it away. Hence the rejection sampling. So the problem with this approach is that it's quite slow. And if Z is high dimensional, C will be massive. And C is also the expected number of draws you have to make to get one non-rejected sample. So this works very well for small models, as we'll see. But for high dimensional models, we have to use a different approach. So I'll just give a little illustration of how rejection sampling works. So here we've got a very complicated density. You couldn't possibly simulate it from it by any other way. So what we're going to do is take a nice simple density, which is just a normal with tails sufficiently heavy that it will always be above the red density. And then we scale it up by the factor C. I can't remember what that was in this case. It was just between 2 and 3, I think. And then we sample from the black density. So we get all these black points. And we scaled them up by the uniform that we're going to use to decide whether or not we should reject the sample. And basically, the rejection turns out to be equivalent to if you are below the red line, then you are accepted. If you're above the red line, you're rejected. So we get this pattern here. And now, hopefully, it's pretty obvious that this set of points under the red curve has the distribution of the target density, i.e. the red density. But maybe you can imagine in higher dimensions, if you know anything about high dimensional geometry, basically the volume of the smaller density will shrink towards 0 very exponentially quickly as you try and bound it with some other density on top. So this does not work well if Z is even medium dimensional, let alone high dimensional. So since we wrote this paper, she came up with a very nice method that just uses inversion and doesn't require any rejection sampling at all. And this is based on the following result that probably everyone did in their undergrad probability class, which says that if you have a CDF for a random variable x, and you have a uniform 0, 1 random variable, and you want a sample from the distribution, all you have to do is invert the CDF, apply it to your uniform random variable, and voila, you'll have a sample from this distribution that's given by the CDF. So if you know the inverse CDF of a random variable, it's very easy to simulate it. For our outcome, if we look at what the conditional distribution of the outcome is given the treatment and the covariate, we just lose the first two factors. So we just are left with this P star piece, which is the causal distribution we want, and in our case, the copula. So, excuse me. So what we can do is replace this with the conditional copula, because Z is fixed, right? So this argument is fixed once we've simulated Z, and then we'll just end up with something like this. So we're going to take our density, we're going to integrate along the second argument from 0 up to whatever quantile it is we want. And this gives us a new conditional copula cumulative distribution function. And to sample from it, all we have to do is sample some independent z's and x's, which, you know, hopefully is relatively straightforward. Sample of independent uniform 0, 1 random variables, and then pass them through the inverse of this guy for the particular zi and xi that it matches up to. And that will mean that now y has the right quantiles in terms of how it's related to x and z. And then we can finally apply the inverse CDF of the margin that we want y to have in the causal distribution. And it should really say yi is equal to this. And then the samples that we get will just look like they came from the distribution we started with. And I sort of, when she told me this, I was like, that doesn't sound like it makes sense, because surely it will just have the ordinary margin that we're specifying here. But of course, because we've already messed around with it here, it doesn't, and it works. And yes, and she sent me a proof, and I was like, okay, yeah, fine. So obviously you may need a numerical method to do the inversion, but it's still much faster than rejection sampling because it's just linear in the number of dimensions, right? I just have to do this once, potentially for every z conditional on the earlier z's. Okay. Right, that's all from me. So I'm going to pass over to She now, and she is going to talk about our package, which is called Causal.
Thanks, Robin. So I'm She. I'm going to introduce our R package called Causal, and also give you a bit more details on how to use this. Cool. So our package is called Causal, and I want to note that the second A in the spelling has been fashionably omitted, and you can install it from GitHub here. So the main function for simulating data is called Frugal param, and it actually takes in 4 important arguments. The first one is the sample size, the second one is formula, and then family and parameters. So this function is very intuitive and straightforward to use once you figure out, or once you are familiar with how to specify these 4 very important arguments. And I'll take you through this. So the first out of 4 important arguments is formulas. And again, it has 4 elements. So we just like 4. The first one should be the formulas for all the covariants, so all the z's, as Robin just mentioned. And then the second component should be the treatment and effect modifiers. So we have to specify how the treatments are assigned, as well as how the effect modifiers are distributed. And the third component is the most important. So this specifies the causal relationship of interest, or this specifies the interventional causal distribution. So here, as we can see, we are interested in the causal distribution y given treatment 1 and treatment 2. The last out of the 4 components should be the copula parameters. So the copula specifies the dependencies between all the z's and the y's. And we can see that all the 4 components, you can either specify them as a single formula, or you can specify at least formulas. And also, as you can see, the copula can depend upon a subset of treatments. This is to see that in the last component, we want the copula correlation matrix to be dependent on the second treatment X2. So now that we have gone through formulas, this argument, it should be fairly easy to introduce the family argument because it follows exactly the same format. And I want to point out that for these 2 arguments, the order is very important. It means that you should specify covariate, treatment, and the outcomes, and then the copula. So remember, the order is very important here. So currently, we implement, we specify the families by integers, and you can see here are the mappings. So for example, if our outcome is Gaussian, then we will put the value 1. And if we want to specify a Gaussian copula, we'll put 1 there, as you can see in the example. So the third very important argument to the function is parameters. So unlike the first 2, the parameters takes in a named list. This means that it's not that strict on the ordering of inputs. As you can see, so for most of the variables, we specify a beta and a phi. So the beta are the regression coefficients. So for example, in the y here, we basically specify the mean of y to be minus 0.5 plus 0.1 times the first treatment plus 0.4 times the second treatment. So we specify the mean like that. And for some distributions, they require a dispersion parameter, and we use phi to specify that. I want to point out that the phi for a normal distribution is actually variance instead of standard deviation, just to be careful of that, because myself have spent quite a bit of time debugging because I forgot that this is actually variance. So these are the 4 very important arguments that we need to put into the main Frugal param function. So hopefully this makes it sound a little bit more easier to use.
So I just noticed there's a mistake on the slide there. So the y argument doesn't end. So there should be phi equals something on the end there. It's just been lost. So that's probably my fault.
Okay, so I will spend time debugging this if I actually coded this up. Cool. Now, next, I will sit down and show you some of the code so that you can be more convinced that it's actually simple and easy to use. So in this demonstration, I will show you how to actually code up the example of dynamic treatment model. So first, we load the causal package along with several other packages. So these packages are just for the separate analysis. These are not required if you just want to use the causal package. So as you can see in this code chunk, I first specified the 4 important arguments that are going into the function. The first one says that we want 1,000 samples. The second one is formula. So if you recall, we have a hidden confounder U. So U is specified in the first element, and then we have the time varying covariate Z. And Z is influenced by treatment A. So this is like whether you took the drug and how your blood sugar corresponds. So this is the first element in formula, and the second element should be how treatment is assigned. So A for 1 means that A is randomized. So first dosage is randomized, and the second dosage is a function of the first dosage and how your blood sugar corresponds. So this is the second component. The third one is the most important because we ask the question of what would they be if we give treatment A and B to everybody. So this is the outcome component. And the last component is the copula dependency. So in this case, U, Z, and Y will enter the copula. And as you can see, we next specify the family argument, and the order of it should follow how we specify the formulas. For example, we have 5 and 5 here. This means the two treatments are binary, and we have 3 here. It means we specify Y to follow a gamma distribution. So next, we specify parameters. As I said, this is a named list. So we say this is the list of parameters we want to give A, and we can realize the order of how we specify things. So once you have these 4 components, it's just as easy as one line of code. So run. Cool. So although Robin said it might be slow, but as you can see, not that slow. So here is what the data set looks like. And then you might have a question of, is the data actually simulating from the model we specified? So we can verify this by fitting a marginal structure model using inverse capacity of treatment weighting, so IPTW. And let's run it, and we can see that the marginal structure model indeed gives us the parameters we specified. So the true parameters should be -0.5, 0.2, 0.3, and 0. So they are all within 2 standard deviations. We can also fit the causal model using the fit causal function in our package. So as we have gone through how to specify the simulation function, it's fairly straightforward. First argument is the input data. The second argument is formulas. So as you can see, it's specified in a similar way, and we don't really need to specify that for treatments. And then family should correspond to how we specify the formulas. And we don't need parameters because that's what we are estimating. So I won't run this chunk just to save 40 seconds of everybody's time. So this is what the output will look like. And you can see the coefficients of the causal relationship that actually follow the true values.
And that's fitting by maximum likelihood.
Yeah, that's right. Cool. And the next example, I just want to show that it's very flexible, and if you are interested in a binary outcome, say maze event as the example Robin just gave, it's really as simple as changing the family of Y to 5, which corresponds to a binary family, and then it's exactly the same. You can just run again. Cool. Next, I will hand it over to Dan to show us the parallel implementation in Python.
Thanks very much, Yi, and good afternoon, everyone. So, well, mainly when developing this sort of Frugal copula package, the real intent there was to look at the rejection sampling approach that Robin originally implemented in Causal and see whether we could make use of the tools in Python to really speed up that process, not only for simulation, but also if we want to do some inference on it as well. Oops. So as I mentioned, this is all found in Python, and the real backend for all of this stuff uses a lot of tools found in the NumPyro and JAX packages. And so, well, the real, of course, you could very much just implement this yourself if you know these two packages quite well. I think the idea of this tool is to act as a wrapper around that, so you don't need to know the really intricate details of those two to get started with it. And all of this can be found on GitHub. Now, the general workflow is slightly different to that in Causal. So as opposed to specifying, say, the family and the parameters, things like that separately, we do it all in sort of one big bulk in a dictionary. And then once that's specified, we pass it through this sort of copula model object where it's read and processed and passed into a JAX format. And then from there, one can very easily just select an arbitrary MC sampler. So I think non-para has a variety of those on hand, and the output is both the fitted model, in which case if you want to do diagnostics to check that the MC chains haven't done anything unexpectedly dubious, you can very easily check that, and also it will give you the simulated samples themselves. So here's a bit of a recap from the previous page. So the main thing I would want to highlight here is that sometimes it's one of the benefits of this sort of MC packages is it can be very easily parallelizable. So if you want to fit do this sampling step, you can parallelize it across your CPU cores. And I say the main thing for anyone who's using this is to make sure that when they import NumPyro at the start, they make sure to add this line underneath. Otherwise, you'll be stuck with only one core when you could be using 4. A lot of the distributions that we're using, as I mentioned, are going to be found in NumPyro. And so basically, you'll all find them in this dist package. The documentation for NumPyro is really fantastic, more detailed. And so there's a richness of different distributions that you can find there, as well as the different parameters that you can specify there as well. So I just took a bit of a snapshot from some of the code that I'll show you later, and it's very much just built from the similar sort of graphical model that she mentioned earlier. So as I mentioned, all of this big bulk of a dictionary is where we specify things, and instead of doing things piecewise, whereas we start with the confounders, then the treatments, then the outcome, we do it all sort of in one big go. And the one thing I would say is that when specifying this dictionary, the keys for your dictionary will be the variable names that you're sampling from, and you need to make sure that when entering these, you enter them in the appropriate topological order of the model. So that's something that ideally I'd like to get rid of, and so it doesn't matter which order you put it on, but for the moment that hasn't been implemented, so proceed with caution there. For specifying these parameters, I think the general input is very much akin to what she discussed with Causal, where you specify a distribution rather, and then you specify a specific formula that corresponds to the particular parameter involved in that distribution. So for the exponential in NumPyro, you parameterize the rate. If this was Gaussian, you would parameterize both the mean and the standard deviation as well. Below that, you can specify the coefficients. One thing I would add, again, to be cautious with, is that JAX only deals with floats. So if you have any integer-based coefficients, just make sure you add a decimal point after there, otherwise it will throw up a bit of a nasty bug. And then after you've specified all those variables, then you start parameterizing the copula, where we have a set of copulas already implemented in Frugal copula, and the variables that one uses, we basically just, you can just specify them. They will, of course, need to have been previously defined earlier. And then likewise, we can specify the functional form that we want those parameters to take and the coefficients that accompany those formulas. So of course, here we're just dealing with constants of the values specified in this coefs box over here. So once that's done, you just pass it through this copula object, and you get your passed Frugal model, and then from that we can just simulate the data accordingly and pull the data out afterwards. So I will give a little bit of a demo just to show that this is something tangible that you can get your hands ready with. So as I mentioned, I think here I've imported a bunch of extra packages as well, but you'll see the main foundation here being the JAX and the NumPyro packages, and of course the functions imported from Frugal copula. I'm simply simulating the same model from the same model that she discussed earlier and that Robin showed earlier in the start of the presentation. So here we have sort of these two treatments, these A and B, and then we have this unknown confounder there with a specific outcome. and you can see that we can very flexibly choose which distributions we're working with. Of course, what we choose to parameterize here will differ from the distributions, but again, these can all be found in the documentation of NumPyro. So if we're simulated from Bernoulli, we parameterize the probs argument. If it's an exponential, we parameterize the rate. And if we have any log inverse link functions that we need to parameterize, this is another constraint. You need to use JAX compatible functions as well. So all of these are, for the main ones, already there. You just need to Google and find them. But if you say just use a regular NumPy exponential function here, that would generate a bug. So here we have two models which are the same graphical model, except for one we have continuous treatment on the top and a discrete treatment on the bottom. We can just run the model and do some checks, diagnostic checks, to make sure the sample is all working in order. And I will hopefully run this without any issue at all. One thing that you may notice for when using this NumPy backend is it sometimes takes a bit of time to initialize and compile the model, but once it's done, sampling from it is generally very fast. So there's a couple of seconds of initialization speed, but if you want to sample from much larger dimensional models or simulate much larger data sets, that scales quite nicely. So I think that's all done. And now if I go back to the original package, I believe it's, no, I scroll down a bit. Oh, here we go. So we're just going to do exactly the same diagnosis test that she did on the causal same samples. Here we just load up these continuous values, and then doing on the continuous outcome data, we see that we also get within two standard deviations of the mean, the correct parameters that we expected at the start. And well, I'm going to skip this fit causal likelihood model, just for the interest of time. And we can also do the same thing with the discrete outcome as well. So in both cases, whether we're dealing with discrete or continuous outcomes, you have a wide degree of flexibility on what you want to fit. And then we wanted to do one final check, which was to verify whether samples from both different methods were basically indistinguishable, just to make sure that even though we get the same causal effect, we're not doing something fishy in the generation of the data. And so we trained a GBM classifier, where we took the two data sets of equal size, put them together, and tried to see whether we could train a model to discriminate between them. So we did a 70-30 test split on the data, and ideally our interest is that they should be indistinguishable, so the accuracy should be very close to 50%, and basically it's just saying there's a coin flip in distinguishing the two, and as you can see, that is very much what happens. So I think that's it from my side. I think the summary really is that whether you're fluent in either R or Python, it's very easy to do both of these things. We're both, well, all three of us are continuously developing this, and so any feedback would be much appreciated. And I think there's also the Frugalverse repo, which I think is it's sort of an online ebook on GitHub. If you search for that, you should be able to find it, and it tries to pull all of these things with a bit more explanation and demos for all of you to use. Thank you very much.
Yeah, so just to add to what Dan's saying, so is someone posted in the chat the link to the Frugalverse book, or
I can do that afterwards. Yeah. I'll just
okay, yeah, we'll post in the chat a link to the book down project. Also, things I sort of thought of as we were going through it. So you can specify link functions in the so it's an optional argument, but it's sort of, you know, would be like the fifth thing if you wanted to specify these models. So we've got these four formulas, four arguments: the sample size, the formulas, the family, the parameters. But you can also have arbitrary link functions as well, in exactly the same way you would in the GLM function. And the other thing is we can have continuous treatments. I think all the examples we showed had binary treatments, but you could easily have a Gaussian treatment as well, and it will work exactly the same. And you can fit it, again, exactly the same, using maximum likelihood if you would like. Okay, I think that's everything. Thanks very much for your attention, and happy to take any questions that you have.
Questions online? Can you give some examples of just what applications you've done the simulation for?
It's a good question. So, I mean, yeah. So, I mean, the idea would be, you know, if you're designing a trial or something, and you have some hunch about what you think the parameters might be, and you've got some tests, you might simulate under a null hypothesis that there's no treatment effect, check that the size of your test is what it's supposed to be, and that would be a way of helping you to plan a power analysis, for example. So you'd say, okay, well, if I have this many samples, am I getting 80% power when I make the effect size 0.5 or whatever? And if not, what do I need to increase it to? So that's the sort of thing I'm envisaging this would be useful for. I guess, what are other applications of being able to simulate this data for?
Can I add to this?
Yeah, please do.
So this is an example or an application I'm currently working on, and I did my time interning at Novo Nordisk. So the question of interest is about data fusion. So what is the best method, and what are the strengths and weaknesses of different data fusion methods when applying to real-world data or to have real-world applications? So I used our package to simulate trial data and real-world data, and then test out all the available data fusion methods that are market to understand what are the weak spots and what are the strengths. So this basically enabled me to encode exactly the causal relationship that I can test for.
Sounds good. Are there any non-medical examples?
Yeah, so well, I mean, you can do sensitivity analysis as another application. So, you know, for example, we can control the propensity model. So you could say, okay, I'm going to fix this marginal structural model and maybe implement the wrong propensity score model and see how that affects my inference, for example. And there's nothing, it doesn't have to be a medical example. It could be any causal example that you're interested in. Other applications would be, so she's mentioned data fusion, but there are also things like there's something called the nested Markov model, and you can simulate from those models quite nicely using the Frugal parameterization as well. And it means that you can do things like model checking. So you might have an idea about what the marginal structural model is, but maybe you don't specify all the parameters correctly. So you can then do something like a likelihood ratio test to say, is the model a good fit with this smaller collection of regressors in it compared to a larger one, and that will tell you whether or not you've specified the model correctly, you know, assuming all the causal assumptions are correct. So there's quite a few different things you can do with it.
I just had a question about the code. I didn't quite follow how you were specifying the copula argument. I was just wondering if you could explain that a little bit more.
So there's a few different ways of doing it, and the syntax isn't entirely consistent. So this is saying that the copula parameters, so this is, we specified before, a Gaussian copula. The parameters here is just the correlation between the quantiles of y and the quantiles of z. It's one parameter. So we're saying here that it is allowed to depend upon the second treatment. It could depend on the first treatment as well. And then what this is saying, so there's a link function which doesn't really appear on here, but you could see it in Dan's code, which is you take, I better not use a marker pen because then people on Teams won't be able to see. So let me see, where is it? Here, right, so this is the link function. So it takes your 0.5, takes the x bit of that, so it maps it to 0, 1, and then it doubles it and subtracts 1, so it then maps it onto 1 minus 1, minus 1, 1. And this is saying that the correlation between the quantiles of z and y is fixed at whatever that is that about 0.3 or something like that, I think. So it's about 0.3 in this case, but it could also depend upon, it's another inconsistency, right? So there should be a second parameter because we put that it's supposed to depend upon x2. So there should be another parameter here because it's supposed to depend upon x2 as well. So it should be, 0.3 plus something which depends upon whether x2 is 1 or 0. And then it would have a different correlation depending on what the value of x2 is. Does that answer your question? Or
No.
Okay, yeah. And then
So what's on where you specify the copula formula, right? You have the twiddle, it's implied that y and z are on the left-hand side of that.
yes, yeah. So basically, if you specify it like this, it means all the covariates and all the outcomes are paired with whatever family you specify.
Mm-hmm.
And you can also have a Vine copula. That would be in the multivariate case. I think, do you have an example of that, or was it Dan?
Not on, but yes, I think it's generally if you want to, if your compounder set joint is specified by a combination of the condition factors, then in order to preserve the dependency structure of the graph, then you will need to use a Vine copula to represent that. However, in the example here, all your compounders are basically, but they only their margins are parameterized, and the dependency between them is specified by the copula, then this approach should work fine.
So I thought, was it in here? You have 111 as your set of parameters for the primary parameters for the copula.
Yeah.
Here, right. So what this is doing, it's maybe not so clear, is actually saying it's a Vine copula. And we've got these three variables, u, l, and z. So u, l, and y. And the first one here is saying, I want the bivariate relationship between u and l, or z, to be a Gaussian. And then the second argument here is saying, I want the marginal relation between u and y to be a Gaussian. And then the third argument is at the next level now. It's saying I want the conditional quantiles for y given u and l given u to also be Gaussian. So this is really the parameter in this case is really the partial correlation between u and l given, sorry, y and l given u. So it's sort of, yeah, you get this additional flexibility if you want to use the extra families. And Vine copulas also have the nice property that they're variation independent. So you can, whereas with a Gaussian, there's a danger you might specify a matrix which isn't positive definite, but if you're using a Vine, that can't happen.
Yes, please.
Thanks. I was wondering if you could just say a little bit more about the advantages of this over what might be sort of like naive baseline, which would be my first thought if I had to tackle this problem and I were unfamiliar with this frugal parameterization, would be to say, just fit them all for every factor, right? If you have the full factorization of the graph.
Yeah.
Right.
So, well, I mean, the obvious answer is then you don't have a nice model for what you're interested in, right? So you would only get, so I mean, yeah, you could do that, right? You could have a logistic regression for y given a, z, and b, but if you're actually interested in is modeling y causally as a logistic regression given a and b, that's not compatible with the broader model where you're specifying a condition on three things to be a logistic regression. It then logically can't be also a logistic regression two things because the logic function is not collapsible. So you can do it, but you don't get the nice elegance of having a particular parametric model that you're able to simulate from. Whether you want to add anything to that, Vanessa?
Yes, and there's the problem of the G9, that you might inadvertently limit your model by specifying the conditionals. You inadvertently limit what the marginal model under intervention can actually do.
Any other comments? Have you been through all the journals and picked up on how their analysis would be different if they did use your models?
Not really, no. I mean, we've seen a few papers where people are doing things and we think, no, that's just wrong. We shouldn't be doing that. I don't know.
Yeah, so the early story of this using marginal structural models, people were simulating to see, because it was a new method in 2005, 6, and around that time. And then they were finding, well, this method doesn't work, but they found this because they were doing the simulations wrong. Because you need to put a bit more thought into actually making sure that you've developed a method of estimating from this model, but you are not simulating from that model because you take a naive approach. And then, of course, the method will look wrong, but it's the wrong simulation.
It could revolutionise any of the pharmaceutical research.
Well, that's what we're hoping. Our Trojan horse of She to go in and get them all using our package.
Yeah, I'm thinking retrospectively as well. Right, any other comments? Okay, well, thank you very much, and thanks very much for a great explanation there, Kim.